first time in China. Today I'd like to tell you about very recent work that just appeared this week about non-planar scattering amplitudes. This is in collaboration with Bernhard Mistelberger, who's a postdoc at CERN. Here he is, and the paper just came out yesterday. It's all very fresh. Let me start with some motivation. The main motivation for this work really is to provide further analytic data for scattering amplitudes. I'm convinced that this is very important. We've seen in the past that having around analytic formulas that one can look at, analyze, is really an important catalyst for progress in developing new methods, understanding more deeply the underlying concepts of quantum field theory. And we've also seen that very often having a simple toy model around is very helpful. And so in that regard, the n equals 4, the maximal supersymmetric Young-Mills theory has been very helpful. And you can really think literally of that as the analog of what the hydrogen atom is for quantum field theory. It's the quantum field theory analog of what the hydrogen atom is for quantum mechanics, in very literally in the sense of the symmetries. And there's many examples of developments. Just think of on-shell methods, for example, recursion relations, generalized unitarity. More recently, also a better understanding of relationship between loop integrands and what the functions are that we get when integrating them. And also not just an understanding, but also concrete methods for obtaining those results. And I think it's fair to say that there's been impressive progress over the last, say, 10 years or so. But mostly it's been limited to the planar sector of the theory. And there are actually fascinating findings also in non-planar, in the non-planar sector, but to date, mostly they've been limited to loop integrands. So the integrand before you actually carry out the integrations. And very few analytic results are known for the integrated answer. To date, there's basically some free-loop form factor, and there's a two-loop four-particle amplitude. But that's more or less it as far as analytic expressions that we can look at, can try to understand, are concerned. And so in this talk, I'm going a step further. I'm going to report on a calculation of a full free-loop four-particle amplitude, where full refers to the color dependence, so we compute all the color structures. Now, thanks to these developments regarding loop integrands, we have many different representations for loop integrand at our disposal, and they're actually very interesting. They manifest various intriguing properties, such as the BCJ duality. There's a form which makes the UV behavior manifest, and more recently, there are representations where the integrand was written in terms of certain D-log forms, which is very important when you are trying to do the integrations. And there's also been an observation in this language of D-logs forms of an absence of certain poles at infinity. However, despite all this nice progress, the main difficulty so far has been the difficult non-planar free-loop integrals. They're just unknown. And so the first step in this project was to tackle these integrals. So they can be organized in terms of these 9 topologies. In the n equals 4 super Young-Mills theory, basically all of these topologies appear with various numerator factors, which then exhibit these properties that I just briefly mentioned on the previous slide. And so what was the status before we started? So in 2013, actually, we did a systematic analysis of this topology A and E, the planar ones, which are much simpler. So those integrals were analytically known by then. And we also saw that in principle, the method that we used, I'm going to say a few more words on what the method is, could also be applied to non-planar integrals, but we only used it for sample integrals. The reason is basically a technical difficulty that these integrals are just very cumbersome. And so in this work, we extended this calculation, which basically began in 2013, together with Volodya-Smirnov, we extended this to all the non-planar families. So in fact, this means that we not only computed the integrals needed for n equals 4 super-Yang-Mills, but actually all possible free loop integrals that you might encounter. So in particular, if you had somewhere in your notebook an integrand, say for a QCD, 4-particle amplitude at a non-planar level, you could equally use our integrals and derive a final expression. But here our motivation was the n equals 4 super-Yang-Mills amplitude. Let me just say a few words about the method. A key point in the method is this better understanding of how certain forms of loop integrands lead to nice integrated expressions. And I just alluded to it earlier. A key concept here is that of so-called leading singularities. And in particular, to choose an integral basis that has so-called unit leading singularities, so where the leading singularities are normalized. Now, I just want to give this is actually a very simple concept. Let me just give an example. So first example will be an integrand which is not of the type that we like. So if you have something like dx over x squared, we don't like double poles. And so this I could write as d of minus 1 over x. This is something, this is not of a type that I like. Instead, what we like are integrands which can be written in terms of certain d-log forms, where here, instead of just a rational function, you'd have a logarithm of something. And just to give you a slightly less trivial example, we could take an integrand depending on 2 variables, x and y, and let's just say it's dx dy over 1 plus xy. And now it's just algebra to see that this can be written as, for example, d log x times d log 1 plus xy. It's not a unique representation, but it is one possible representation. And so what's important here is that this is one of these d-logs forms I mentioned. And the prefactor, there is no prefactor actually. So in general, we want kinematic independent prefactors. So for example, we could, in such an integral, we could have, instead of this 1, some kinematic variable, but it would then be contained in the logarithm. There wouldn't be any additional factors. So this is this concept of d-log forms, or said differently in terms of singularities. If we take maximal residues of this integrand, we just get some constants. So you should think of these examples as some toy version of an actual loop integrand written in momentum space, where you say at the one loop level you have 4 integrations and you can take 4 residues, and so the integrands we like are those where upon taking these maximum residues you just get constants. So what this means is that we choose a basis that has these properties. Typically, if you have a certain loop integral, it amounts to making an ansatz for the numerator and then choosing the coefficients in the numerator such that the ansatz satisfies these criteria. So this is an essential part of a method. We started with those topologies and chose integrals which had these properties. Now, why is this useful? It was observed back in 2013 that if you compute differential equations of integrals of that type, then the differential equations take a very simple form. And so in this particular case, we find these equations here. So f is a vector which contains all the basis integrals that we need to compute. They depend on a dimensionless variable t over s, where t and s are the Mandelstam variables, and on the dimensional organization parameter. And so you see it just takes this very simple form here, which is actually a Knizhnik-Zamolodchikov equation. I won't go into too much detail about this equation, but let me just say that in a Laurent expansion epsilon, it's trivial to solve. You just solve it order by order. The reason it's trivial to solve is that the right-hand side always decouples order by order. The other thing we need to know is about the boundary conditions. This is another nice feature of this method, that it turns out that almost all of the boundary conditions can be obtained from certain consistency requirements and symmetry. So symmetry, that certain graphs are obtained from other ones upon exchanging external legs. And consistency, the absence of certain unphysical poles. And so for that reason, we can actually show that all integration constants can be expressed just in terms of so-called multiple zeta values. It's also kind of a nice statement from a number theoretic point of view. So having said that, the boundary conditions are under control, and we can write down the solution in a Laurent expansion. The functions we obtain are certain generalizations of polylogarithms. They're in a class of functions called harmonic polylogarithms. If somebody asks you what is this class of functions, there's a nice way to characterize it by looking at what singularities can appear. It turns out that the singularities are just at physical places, s equals 0, u equals 0, and t equals 0. So it's kind of a minimal set of functions that you might have guessed could appear in such four-particle processes. So let me just give you an example. Before coming to the example, I should say this is the method. Basically, I mentioned we did this also as a proof of principle back in 2013, but there was a technical difficulty that these integrals are very elaborate. And in particular, in order to go through this method, there's a technical step which is to process certain identities that Feynman integrals satisfy, a so-called integration by parts identities. And this is nothing particularly fancy, but it requires a large amount of computer algebra. And for this project, there are public codes available for dealing with this, but we used a private implementation by Bernhard Mistelberger, which was faster than those codes. Still, we needed to get a little bit extra help, and the extra help is here. Thanks to Mainz University, we had this, you might not see it very well, but this tiny slot there represents a compute server that we had and that did a really hard job in this calculation. So thanks to all this help, we could actually set up these differential equations and then solve them. Now let me just give you an example, just so you get a flavor of how the results look like. So here's one of these non-planar topologies. And so the example of making this integral to have unit leading singularities, for that we insert a numerator. So without the numerator, this would not be a good integral. We'd get a very complicated differential equation. But choosing this numerator, we can show that it has these properties. We get the nice equations, and then we can compute the integral. And as a result of this choice, it has the answer has some very nice properties. It has a property of so-called uniform weight. One can assign a transcendental weight to the functions appearing here, which basically, these indices basically tell you what the number of integrations is. And you will see that here we just have a constant. Here we have basically one integration. Here we have two integrations. Here we have three integrations. And actually, if you also assign a weight to epsilon, if you assign weight -1 to epsilon, then this whole expression actually has uniform weight 6 in the whole Laurent expansion. So this is something that follows from the differential equation that we have. So all our results are expressed in this way. We compute them up to the finite order. In principle, we can go further, but this is sufficient for computing the amplitudes. Okay, so now let's use these integrals and go back to these non-planar integrals. So again, just the kinematics is that we have the two Mandelstam variables. We compute the amplitude and dimensional regularization, and we parameterize the expansion, the coupling in this way. So now we'll focus mostly on these coefficients in the loop expansion. Kappa here is basically some kind of, it's a factor which is essentially a tree-level amplitude which absorbs the helicity information, such that actually this A tilde here is permutation invariant. So kappa is chosen in a way that this is permutation invariant. An important part of this calculation is color dependence. So we work in SUN, and we have to choose a basis to express our amplitudes in. We choose a trace basis which is formed of single traces and double traces. So our amplitudes will be a vector with 6 elements. Moreover, we can expand in the number of colors n. this formula looks a little bit complicated. So the first line is just refers to the single trace terms. The second line refers to the double trace terms. And basically, one can show that the expansion n goes in powers of 2. So there's a leading color term, and then there's sub-leading color terms. So let me show you what this means. That this actually means up to 3 loops. So we have always at any loop order we have a leading color term, and then we have certain sub-leading color terms, which are represented here. However, there's actually color identities, such as, for example, the photon decoupling identity, and further identities. And at the one loop level, for example, it tells you that these double trace terms here are just determined by the leading color terms. So actually, there's much fewer independent components. We don't have to, not all of these components are independent. Turns out that these components in green are dependent. They follow from identities like this one, and the independent components are these 3. 1 new component at 2 loops, and 2 new components at 3 loops. So this is really the essential new part that we want to compute. Now, we can learn a lot from these amplitudes, and the first thing that you can learn about is the infrared structure. So on general grounds, it's known how infrared divergences look like. They're controlled by a renormalization group equation for Wilson loops. And from this, you can see that they exponentiate in this way. In n equals 4 super-Yang-Mills, there's simplification. The coupling doesn't run, so this integral can be just carried out. And one gets this formula here. And now there's something very interesting. Up to 2 loops, it was shown previously that that only these 2 terms here appear, and this is the so-called dipole formula. Here the t's, they are operators which act on the color basis. So basically this operator here, it acts on lines I and j. It emits a gluon from line I, and it's absorbed by line j. So it's a correlation between 2 lines. That's why it's a dipole term. So up to 2 loops, there's only terms coupling 2 external lines. And what's very interesting, there were certain conjectures that perhaps this might extend to higher loop orders, but as of last year, we know that this is not the case. There's a definite correction at the 3 loop order that was computed by these people. And now this is for the first time, we can actually independently verify this formula because our amplitude is sensitive to that. So on the next page, on the next slide, I'll show you what this formula looks like. Here it is. So here you see you now also have correlations between 4 lines, and you can represent them. They were computed via certain Wilson line correlators, where 4 lines are coupled in such a way, as you can see here. So these people computed this full amplitude. There's something subtle happening when we extract the n equals 4 part, because we have to analytically continue their result. This has to do with the fact that so they write the answer in terms of general kinematics, where all the Sij are negative. But for us, we have S and T negative, but U has to be positive because we have momentum conservation, so S plus T plus U is 0. So because of that, we have to perform an analytic continuation, and what this implies is that although this formula here is real valued, we get certain imaginary parts which are here. So in case you wonder where they come from, this is the reason. So we expand our amplitude to this order. This formula has to do with single poles, and we verify this formula. We find perfect agreement with this reference up here. Now we can go beyond the infrared divergent part and look at the finite part. So knowing how the infrared divergences look like, we can subtract them and define a hard function in this way. Let me just remind you that in the planar case, this is something very simple. So famously, the form of the leading color contribution was conjectured by Byrne, Dixon, Smirnov, and then just a few years later, it was proven through a Ward identity. So this is really remarkably simple. You see that there's only logarithms appearing. Unfortunately, non-planar is not that simple, but now for the first time we can actually look at it in detail. So I explained to you there's these 3 new contributions, 1 at the 2-loop level and 2 at the 3-loop level. So let's just look at them. here's what we have at a two-loop level. What can we see? So there's a couple of nice features here. First of all, again, this result has a uniform weight. It's a uniform weight 6 function. Because it's a non-planar amplitude, there's both a real and an imaginary part. Furthermore, you can see that I've split the result into 2 terms. There's a 1 over x and a 1 over 1 plus x term. If you think about it, it's actually remarkable that only these 2 structures appear. If you went to QCD and looked at a generic amplitude, you'd find many more rational structures. So the fact that only these 2 structures appears actually could be anticipated by looking at the loop integrand, where you find that if you compute leading singularities, these are precisely the factors that come out. So this was a conjecture that this should also carry over to the integrated level, and we indeed see that it's the case. So this is the two-loop function. Now, oh, I'm sorry, I think I said this had weight 6. This is actually weight 4. This is the two-loop function. Similarly, the three-loop functions can be represented in a similar way, but they have weight 6. I just didn't put them on a slide because they're a little longer. So, all right. So we have these functions. Now, there's something else we can do that's interesting. There's a simplifying limit, namely the Regge limit, for which a lot of information exists. So we take S much bigger than t, and in this limit, it's actually useful to slightly change the color representation that we had previously. It's kind of useful to, so we take S very large. It's kind of useful to choose a color basis according to the irreducible structures that can appear in the T channel. So that's what we do now. And then, so when we have 6 color channels, one of them is this antisymmetric octet. And in this channel, we find that there's a very simple behavior, that the amplitude can be just written in this way with a certain exponential. So what this illustrates is that you can use a result to derive predictions for Regge theory and then try to match that with what you expect from other calculations. So here it's just for illustration the octet channel. Let me just on the next slide show you the result in a different way, also including for all channels. So here I've written again, just a finite part of the amplitude, and I've written here all the logarithmically enhanced terms in terms of certain color operators. So here at 2 loops, we just have an operator which is T. T is actually this operator here. This is diagonal in our basis. This is diagonal in our T-channel basis. So this just contributes to the octet that we've just seen. Likewise, at 3 loops, we have these terms here, log squared contribution here, single log contribution here. And so all the terms that you see which have just a single T, those are the only terms that contribute to this octet channel that we've just seen. Turns out all the other color operators, they don't contribute to the octet. But they do contribute to other channels. So here I'd just like to highlight there's this contribution here, this commutator S squared T. This corresponds to the 10 plus 10 bar channel, and is actually the only contribution that's the only contribution in that channel. So having this information, we actually compared with some of the literature on Regge limits. So previously, there's a very nice paper from 2013 by Simon Caron-Huot, who gives a prediction for all the next to leading logarithms in the Regge limit. So this means next to leading at 3 loops, leading would be log cubed, and next to leading is log squared. So we compared with his log squared prediction, finding perfect agreement. And communicating with Simon, we found out that he and some of his collaborators actually have some upcoming work where they predict also the next to leading coefficient for this color structure here. So we also compared with that, and we found perfect agreement. I think beyond that, this is this is, should be then considered as useful information for people who are interested in the Reggie limit. There's some more terms that one can match to try to explain using Reggie theory. So this already brings me to the conclusions. So I've presented you for the first time a full result for free loop 4-gluon scattering amplitude. I think that's a milestone in calculations in perturbative quantum field theory. We used this result to independently verify the 3-loop soft anomalous dimension matrix, which predicts all infrared divergences for massless 4-particle amplitudes. And the result by Gardia, in fact, predicts the result for n-particle amplitudes. We verified the 4-particle case. I should say that actually this term that couples 4 lines is not specific to n equals 4 super Yang-Mills. It can actually be seen that that part is independent of the theory that you're computing in. And finally, this comes back to my initial motivation, I think this provides a very non-trivial data point for future investigations. I mentioned already Reggie practitioners that might find this useful to compare against their predictions, but also I think it's a challenge for string theorists or people who try to use integrability to predict results for scattering amplitudes. Thank you very much.
I'm trying to understand why you specialized to SU3. Is it because you have QCD in the back of your mind?
Oh, yeah, very good. I didn't say this. So here in fact, we follow the literature in a certain way. The decomposition is still general for SUN. It's somehow customary, at least in the Reggie literature, to when one talks about this color decomposition, to label the channels by the dimensionality that you would have for SU3. It's a little bit absurd. In particular, there's a channel which is called 0, which for SU3 is absent. So in fact, this analysis is general for SUN. It's just this labeling is somehow inspired by SU3, if you like.
Okay, let's thank our speaker again.